So, okay, let's start. Let's hope the microphone is not too noisy and that the recording works today. Okay. Today we will touch two different things. First, I will go in less than 1 hour to talk about everything there is to know, a very quick intro to X-ray imaging. And then we will switch to the first part of laboratory experience, where we will have some Jupyter notebooks about, this time, the basics of image processing and visualization and so on, just to familiarize with the concepts that I introduced in the previous lecture. So let's start with X-ray. So X-rays were invented meaning the devices to generate them, or discovered in 1895, and they were discovered by using these devices, which were called which are called, because they still work the same way, vacuum tubes. These are also the same devices that were used as so-called valves or tubes for the earlier computers before the transistor came. And what you have is a vacuum tube made out of glass, where you have two electrodes, and you have electrons traveling from one side to the other, and then emitting X-rays when they stop. They were developing these kind of tubes for other reasons, and it turned out that they produced the X-rays. So 2 months after the discoveries, they were already publishing a paper about it, where there was the X-ray picture of the wife of Röntgen, with where you could see the bones of the hand, and also, if you look closely, the wedding ring. Now, what are X-rays? X-rays are electromagnetic radiation, like light or radio waves or everything like that. Electromagnetic waves work depending on the frequency or the wavelength. They go from many kilometers to nanometers, and their properties change quite a lot. We have visible light here in a very, very, very small part of the spectrum. And so at these kind of energies are proportional to frequencies. These, they behave much more like particles than waves. The wavelength with which we work is between 10 to 0.1 nanometers. And as I said, the energy of a ray, of a wave, is proportional to the frequency. Generally, we use the electron volt as a unit of measure. Now, how do we produce X-rays? We have a vacuum tube, like we said. And inside this vacuum tube, we have a filament, like a proper electrical wire, where you have which, when heated, it emits electron. Now, if you are in vacuum, the electrons can float around in the air. The electrons are negatively charged particles, and so if you apply a difference of potential, they get accelerated quite a lot to the other electrode, which generates the potential difference. So if you put a tension of 100 kilovolts, you will have electrons that arrive there with an energy of 100 kilo electron volts. And then when they hit this piece of metal, they just decelerate very quickly. And they emit a bit of, they lose a very small part of their energy in emitting X-rays from braking radiation, it's called, which is, the actual technical term is Bremsstrahlung, because it was discovered by German people, so they use this very weird term, which is German for radiation due to braking. Of course, the most energy they can emit is the potential difference. As I said, they emit in using X-rays a very small percentage of their energy, which means that there will be a lot of heat to be dissipated, and typical potential values go from 30, which is very rare, maybe only mammography, to 140 kV, which are used only in CT imaging. And the current goes from 1 milliampere to 1 ampere. If you think about it, when you have 140 kV times 1 ampere of current, this means 140 kilowatts of energy being dissipated on a very, very small spot, like half a millimeter of radius, which means really a lot of energy. So if you take an X-ray tube used in a CT scanner, which is the one that uses most energy, after 1 or 2 years of use, it will break the metal, and you will see really the metal which has been excavated by the very energetic electron ray. Now, all the electrons get the same energy, but when breaking, they will emit a spectrum of X-ray energies, where, of course, the maximum possible energy will be the energy that you set on the tube, but the spectrum will have some continuous shape plus some peaks due to the material of the anode. These are some physical phenomena which are not super relevant for us, but you can see that by changing the energy of the tube, you can get quite different spectrum with a higher percentage of high energy rays. Now, what happens when you have some X-rays traveling through matter? They attenuate. So if you have a beam of intensity I0, it goes through some material of thickness X, and the material has an attenuation coefficient called mu. You will get an energy of intensity, which is just the exponential decay. What happens if you have a composite object? You have the integral, or if you have a piecewise constant material, just a sum like this, of the attenuation due to all the materials. This is relatively trivial. Now, how can we use that to generate an image? Of course, we can act only on the coefficient, on the attenuation coefficient. And it turns out that at the energy that we are working with, this is a log scale, we go from 10 kV to 100 kV. We've seen before that if you set a tube to 100 kV, you get all the energies in this kind of range here. We have very different attenuation coefficient for all these kind of tissues. We have fat, adipose tissue, blood, cortical bone, which is the hardest one, water, which is present in a lot of parts of biological tissues, lungs, and trabecular bone, which is the soft part of the bone. However, what happens if you divide this attenuation coefficient by the density of each one of these material? Most of the material, given that biological tissues are all made of carbon, oxygen, and hydrogen, mostly, and some trace elements, mostly in the same proportions, it turns out that the attenuation coefficient, all the lines there superimpose. So it turns out that the attenuation, with the exclusion of bones and a very minor difference in fat, their attenuation coefficients depend exclusively or mostly on the density of an object, like grams per cubic centimeter of an object. So how do you get an image from there? You have a source of X-rays, your X-ray tube. And if you have the X-rays are generated from a very small spot, you just need to focus the electron beam on a spot which is, I don't know, less than 1 millimeter, depends on your application. You have a source of X-rays that travel propagating along straight lines, so around the cone. Then you have, then they hit a target, and they get, and behind the target you put a detector. A detector used to be a film, like a photographic film with very small differences. Nowadays, it's a camera detector made exactly the same way of your actual phone camera detector. It's a CMOS detector with pixels and everything else. And in every pixel, you get a signal which is proportional to the number of X-ray that arrived in that pixel. So what does this mean? That if you have a ray traveling from here to here, and then traveling inside lungs, which are not dense at all, it will have very little attenuation, so you will get a high signal in the detector. If it travels along bones and tissues, it will have much more attenuation, so you will get much less X-rays on the detector, so you will get a different signal. So in X-rays, these are called planar X-rays because the image you get is a plane. You get a projection of every pixel contains information about the density, the cumulative density of all the material along which the beam passed on. This is the color scale that generally is used to visualize the image. Related to that, because historically the detectors used were film negatives, which meant that the more in a film negative, the more light you get, the darker the film becomes. And this is the way that physicians were trained to evaluate the images. With black, you got air. If you have only air between the source and the detector, you have no attenuation. You get lots of X-rays, and so the film becomes black. If you have some attenuation, like if you have fat, you get some dark gray because you still get lots of photons. If you have muscle, you have some attenuation, and you get gray. If you have soft bone, you have much more attenuation, but you still get some X-rays and you get almost white. If you have hard bone, which stops all the photons, you get completely white. Now we have, I've shown here a possible use of the fact that you have a detector on one side and the source on one side and the detector on the other. We have some, when we take what's called in the medical field a projection, because this works like a mathematical projection if you prefer that, you get some magnification, and this is something you can exploit. Let's say that you have what's called an anterior-posterior projection. You have the X-rays that comes from the anterior part of the body, which is the anatomical term for, say, the front. And you get diverging X-rays going here, so the apparent heart size is bigger. If you have the same person switch the other way with the heart closer to the detector, you get a smaller apparent heart size. Now, this is what a typical, this is called the lateral projection, which means from the side. Image of the thorax looks like. And we will have more examples during the residual part of this lecture. You see really lots of details. It's really difficult to interpret these images, and that's why radiologists need 5 years of training, because they need to learn to do some pattern recognition. If you look well, you actually see 2 lines of ribs, and you can see that and by recognizing them, the smaller ones are the one closer to the detector. The larger ones are the farther ones. You see this marker L here. This is put by the radiation technologist during the acquisition. They put a marker on top of the detector with L or R to identify the direction in which it was acquired. Now, what do they do, the physicians? Now, once the physician can say, okay, we have a mass here. Say, okay, assuming that it is on the lungs, it must be on the right, because otherwise it will be outside the ribs. So this is just an example of how complex these images are to be interpreted. Let's take a look at some example images. Now, when many people think about planar X-ray, they think about these kind of images here, which if you don't have any kind of medical experience, you can say, okay, there's a broken bone. And it's not very difficult to understand that. The thing is that a typical image is actually like that, and here there is actually a pathological finding, but I guess it will be pretty hard for you to identify where. Anyone wants to take a guess? This one? Actually, you're right. Many people miss this, or because you might perceive slightly a line here, highlighted here, but this is just vascularization, actually, while the very small change in density here, which we have highlighted here, is a stress reaction. This is a problem due to, is a kind of a fracture of a broken bone due to maybe excessive stress put on it, physical stress put on it. And of course, this is why I was saying that even for bone imaging, which is the easiest part, you really need, physicians really need a lot of training, because the findings are pretty hard to determine. And you need really lots of experience on what is a normal image. Now, I guess this is the most used imaging exam used in hospital for whatever reasons. And I have a slide I will have some reason for that. And this is generally acquired in breath hold. You tell the patient to hold their breath. Why? Because otherwise the organs move and you get a lot of blurring. And you can identify, with this very simple exam, you can identify really lots of features. You can identify the heart. You can see if the heart is of normal size or it has some other issues. You can see the spine if the position is correct, the stomach, the liver. You can see the presence of great vessels like the aorta and things like that. This is a normal abdomen or the pelvis, sorry. And here it's more complex to interpret this, because in the thorax we have the lungs, which have extremely little X-ray attenuation, so you see a very high contrast between the structures where something is present or not. If you have a nodule in the middle of the lungs, it pops up immediately. While here you have lots of organs. And so the image is pretty crowded and it's difficult to distinguish features. But still you can see well, not you maybe, but not me also, but a physician can distinguish the two kidneys, the contours of the liver, the spleen, of course the bones of the pelvis, and you also some other features like feces, or these very large blobs here actually is just bowel gas, which shows up extremely well in X-ray imaging. Now, let's go to review the applications. As we said, X-rays are attenuated mostly by density. So they are useful to detect everything that is related to density, because the contrast we will get is indeed density contrast. This imaging methodology has a very high resolution. It's common to get up to 3 pairs of lines, which is a definition of resolution, which means that you have a black and a white line next to each other. How small can they be when you still distinguish them? You can get 3 pairs per millimeter using detector pixels as small as 170 micrometers. There are lots of possible applications. Bone fractures, of course, because bone are very dense and very attenuating, so you can see their changes in shape pretty easily. Abnormal masses, if you have something which was not present and appears, usually you see it. It's useful in pneumonia because pneumonia acts on the lung, so it changes the features in a very identifiable way. You can use it to see the presence of foreign objects, dental problems due to the density, calcifications, because if you have a calcium plaque in the heart, for example, or it's a bit denser, but also it changes the atomic composition, so it has a lot of attenuation. Now, the pros of these methodologies is that it is very cheap, very fast, and very low radiation. This is a typical X-ray imaging setup, an all-purpose imaging setup, because you have an X-ray tube, which can also rotate. Then you have a bed with a detector under it. So if you need to acquire, I don't know, a broken arm, you can tell the patient to just put your arm here. If a bone, you can just have the patient lie down, the pelvis. Or if you need to do spine imaging or lung imaging, you can use this other detector, which is straight on the wall. So you can do upright standing imaging. A setup like that probably is around 50,000 euros. So it lasts for a decade or more, or 2 decades. And it's incredibly fast. The time it takes to take an image is some milliseconds. So most of the time is patient positioning. So if you are quick enough in positioning the patients, you can do like 7 patients per hour or something like that. It takes more time to read the image than to acquire it. It has extremely little radiation. And it's just to give you an idea, when I say cheap, I don't know this year figure, but I guess the standardized reimbursement in Italy for an X-ray of the thorax acquired from the front and from the side was 10 euros. And you can get information about really lots of pathology on if everything is all right. So you can see why it's used for in every possible context in hospitals, because it's so simple and common and still very informative. The downside of these methodics is that it gives you only 2D images where lots of information can be superimposed one another, difficult to recognize. And of course, it cannot diagnose everything. Only things that you can see with changes in contrast. Now, another application is mammography. Here we use, given that the amount of tissue that the X-ray needs to go through is a couple of centimeters, not a whole thorax or a whole abdomen, we can use much lower X-ray energy. If you remember the plots, we have a much higher contrast between different tissues, the lower the energy that we use. And also using dedicated detectors, we can get extremely high spatial resolution. We can get to a resolution of 10 up to 10 pairs of line per millimeter. And this is an example. This is probably an image acquired already 10 years ago, so not even state of the art. You can see the appearance of calcifications or dense mass with an extremely cheap exam, and we can see them super effectively. We can see here, given that in breast the tissue is mostly made of fat, the contrast here between this is vascularization and probably this is the come si dice ghiandola in inglese? Sorry, I'm really missing the word. The gland, of course. The contrast between the fat and the gland is very high, and the vascularization at this low energy, X-ray energy, the contrast is very high, so you can identify features, identify changes in morphology extremely soon with a quite cheap exam, which makes it useful for screening purposes, where the a priori probability of a finding is very low. Now, another application is fluoroscopy. It takes the name from the technical devices used before the advent of digital detectors. And now the term is still used, even if we don't use fluoroscopes anymore, to mean real-time imaging. The difference with what we were doing before is that when you go to take an X-ray of the thorax, you take a shot, you take an image, and you're done. Here you have a continuous X-ray shooting, continuously shown on a screen in real time, and it has multiple applications. Generally, is one of the most common application is visual to a positioning during medical operations. So you're doing, I don't know, you're positioning a prosthesis in the bones of a patient during an orthopedic operation. You need to know if the bones are perfectly aligned to the prosthesis, and you keep on shooting with your X-ray and seeing what you're positioning. Also for some kind of non-invasive operation where you insert it into the body a very small, like in a great vessel, a very small survey camera, and you want to see where it's moving within the body because you're operating it from the outside. And then one of the most important application is during angiography, which is the study of vessels. And here the physicians inject some contrast media, which is a substance which travels within the blood and has a very high X-ray absorption coefficient. And so what you can do is to take an image here, then you take a second image with the contrast media injected into the arteries or veins according to what you're studying. You see the difference in X-ray contrast here. And once, when there were TV cameras looking at the fluoroscopes, you will need to do a diagnosis taking a look at images like that. Nowadays, if in the digital world, if you have these two images, you can just take the difference numerically on a computer, and you can see the vessels with super great details. This is especially useful for cardiac studies when they have to open your coronaries by placing your stent. By injecting the contrast media like that, you can see where obstructions are. Do you have any question until now? Okay, I wanted now to introduce you a challenge that was an important imaging challenge launched a couple of years ago, from which we will use some data for the rest of the course, sometimes to do our experiments. It was the pneumothorax challenge. Now, pneumothorax is a disease where air fills the cavity between the pleura and the lungs. The pleura is a kind of very thin films that covers the lungs. And when there is air between the pleura and the lung is compressed, so it cannot work well. The prevalence is about of 20 cases every 100,000 persons per year, but it's potentially fatal, so it's extremely important to have a very quick diagnosis. Now, given that you need a very quick diagnosis, what's better than planar X-rays? So this is a typical scan of a pneumothorax, of a full pneumothorax, which means that the left lung completely collapsed here. By the way, in medical imaging, due to historical reason, generally the left and the right are seen flipped. So when you take a look at the image, this is the left side and this is the right side. And how do you recognize that? Because you see the lungs as black. Why is that? Because there is something in a lung, but which has some small attenuation, like you can see here, the bronchi and other things. If the lung is collapsed, instead you have exclusively air, so you can recognize it that way, but also to the fact, in this case, that some structure have been shifted by the pressure, so the trachea and the heart are to the right compared to where they will be supposed to. Now, however, there are also cases where you don't have a full collapse, and again, this is just to show you how hard can it be also without training, but even with training, I guess. Here, the sign that the physicians look for is the presence of a thin line, which maybe you can see here, which means that the lung is 2 centimeters away from the border between the lungs and the rib cage. Now, what was this challenge, for which I have here the link? The basic idea was that they wanted to develop an early warning system, because in an hospital you acquire, I don't know, let's say some hundreds of X-ray, of thorax X-rays each day. And they are read with the orders according to which they're read can be pretty random. And so what they wanted to develop was an early warning system that, by an automated scanning of each image, told physicians, here there is a suspect urgent finding, please read these as the first, put it very high on the priority list. And so they they made publicly available 11,000 images subjects with of normal and of subjects with pneumothorax or without, and a manual segmentation. By the way, are you all aware of what segmentation is? Have you done some segmentation courses? Okay. Well, not full courses on that, but okay. And we have masks, so you can, and these are very useful for us to see, to get used to what kind of operations are done on these images. This challenge, I think it was 2017 or 2018, I don't remember. And nowadays, early warning systems for pneumothorax are already commercial. So they are, they went pretty quickly from very difficult artificial intelligence task, if you want, to advanced solution to state-of-the-art device which is commercial, to the commercial level. So it's a pretty amazing development of this field, especially if you remember how hard it is to detect the finding. Okay, so that's everything I had to say about X-rays. I was mentioned before all of you arrived that we had some, that what we wanted to do today, after this theory part ended, is to start playing with images, and I would like to leave you at around 3 p.m. because we have a department meeting. And okay, so let me stop the recording and make a fresh one, hoping